Today we will be looking at Ampere's circuital law and some of its applications. Like Gauss law in electrostatics, which is used to find electric field in case of complex problems and in cases where you are dealing with symmetrical conditions. Magnetostatics, we are using Ampere's circuital law or Ampere's work law. So according to Ampere's circuital law, the line integral of magnetic flux field intensity capital H around a closed path is equal to the direct current enclosed by the path. That is, line integral H dot dl is equal to I. This is the mathematical representation of Ampere's circuital law. And this law is really very helpful to determine magnetic field intensity when the current distribution is symmetrical. So according to Ampere's circuital law, you are going to find the magnetic field intensity around a closed path. And according to the law, the magnetic field intensity around a closed path will be equal to the current, that is the direct current enclosed by the path. Now we will look at the proof of Ampere's circuital law. Consider a long straight conductor carrying direct current I placed along z-axis as shown in the figure. Now consider a closed circular path which is having a radius r and enclosing the straight line conductor carrying the direct current I. Now the point P that you are considering is at a perpendicular distance r from the conductor. And now consider an elemental length dl at point P, which is in the a phi direction, that is in the angular direction, tangential to the circular path at point P. So when you take the elemental length dl, you can note here that since your conductor is in z-axis, it is not depending upon x or y or z, x and y directions. That is, in this case, since you are dealing with circular coordinates, your dl can be written as drar plus r d phi a phi plus dz az. So here it is not varying according to x-axis, that is dx element is not there, and it is not varying according to z-axis also. So dl is equal to r into d phi into a phi, that is you will be having only the middle term when you write dl. drar term and dz az term is neglected since dl is not depending on either of them. While H obtained at point P from Biot-Servet law due to infinitely long straight conductor is known to us, we have dealt with that in our previous classes. So according to that, our final output of the derivation was H equals I by 2 pi r into a phi. So when you know H and when you know dl, you can directly find H dot dl and take the cyclic integral, that is contour integral over phi, and check whether it is equal to I. Now we will move on to the derivation. You know H for a infinitely long straight line conductor is I by 2 pi r a phi and dl is r into d phi a phi. So when you take the dot product of that, a phi dot a phi is 1 as you know, and the remaining portion is I by 2 pi into d phi. Now integrating H dot dl over the entire path, that is over phi from 0 to 2 pi, the only thing that remains within the integral is d phi. Rest I by 2 pi you can take outside, and I by 2 pi into integral d phi from 0 to 2 pi will yield the answer as I, which is the total current carried by the conductor. This proves that the integral H dot dl along the closed path gives the direct current enclosed by the path. Now for proofs, we will consider the path that is selected to be as Amperian path, which is similar to Gaussian surface, while you use Gauss law for finding complex problems electric field intensity. Similarly, here we will be using a term called Amperian path. Now we will look into the steps that are used to apply Ampere's circuital law. So, like I said, step 1 is to consider a perfectly symmetrical path that encloses our direct current I1s, which is termed as the Amperian path. Now, step 2 is to consider differential length dl depending upon the coordinate system that you are dealing with. And step 3 is to identify the symmetry and find in which direction h exists according to the coordinate system used. Now, if you find h, what is our next step? You have to take h dot dl. So, our step 4 is to find h dot dl, that is the dot product, and make sure that dl and h are in same direction. Now, step 5 is the final step where you find the integral of h dot dl around the closed path that is assumed, and you have to equate that to I. So, our Ampere's law is that line integral h dot dl is equal to I. So, our final step is to find integral h dot dl and equate that to I. So, solving this for magnetic field intensity due to direct current I, h should be either tangential or normal to the path at each point of closed path, and the magnitude of h must be same at all points of the path where h is tangential. Thus, identifying symmetry and identifying the components of h present plays an important role while applying Ampere's circuital law. Now, we will discuss different application of Ampere's circuital law. Like we discussed in the application of Biot-Savart law, our first aim is to find magnetic field intensity due to infinitely long straight conductor using applications of Ampere's circuital law. Now, here also consider an infinitely long straight conductor which is preferably placed on the z-axis, which is also carrying a direct current I. Now, we are going to find the magnetic field intensity at point P, and the radius of the path that you are assumed is r. The magnitude of h depends on r, and the direction is always tangential to the closed path, that is a phi. So, h has only component in a phi direction, and that is h phi. So, you will not be having h in the other directions, that is hr ar and hz az will be absent while writing equations of h. Similar is the case with dl2. You will be having component only in a phi direction, since dl a phi is the tangential component at dl. So, you will not have dr ar term and dz az term while writing dl. So, you know the value of h, you know the value of dl. H is h phi a phi and dl is r d phi a phi. Now, to take h dot dl, take h phi a phi dot r d phi a phi, which is equal to h phi into r d phi. As you know, a phi dot a phi is equal to 1. Now, according to Ampere's circuital law, our step 5 is to equate integral h dot dl to I. While doing so, you can write integral h phi r d phi from 0 to 2 pi is equal to I. And noting here that h phi and r are constants, and the only thing remaining in the integral is d phi. When you integrate d phi, you get phi from the range 0 to 2 pi. While applying limits, its value is 2 pi. And finally, what you get is h phi is equal to I by 2 pi r. And you know the magnetic field intensity at point P is only a function of phi alone. So, h is equal to h phi a phi, which is equal to I by 2 pi r, similar to what we obtained in the previous case using Biot-Savart law. Note here that the unit of h is ampere per meter. So, h is equal to I by 2 pi r a phi amperes per meter. Now, we will look at case 2, magnetic field intensity due to a coaxial cable. Consider a coaxial cable. its inner conductor is solid with radius A and carrying direct current I. The outer conductor is in the form of concentric cylinder, as you know, and here we are assuming the inner radius of the outer cylinder to be B and its outer radius preferably C. This cable is placed along Z axis. Note that the current I is uniformly distributed in the inner conductor, and while minus I is the current that is uniformly distributed in the outer conductor. So you have to make this point clear that current I is flowing through the inner conductor and the current which is in the opposite direction, that is minus I, is uniformly distributed in the outer conductor. And here you assume the space between inner and outer conductor is filled with dielectric, say air. The calculation of H is divided corresponding to the various regions of cable, that is, you will be choosing Amperian path according to the different regions of the cable. So in our first case, R is less than A. R is the radius of the Amperian path that you are considering, and A is the radius of your inner conductor. So here the Amperian path that you are choosing is having a radius which is less than the conductor radius that you are considering. That is, R is less than A is our case 1. Now the area of cross section enclosed is pi r square meter square by the Amperian path, while the total current flowing is I through the area pi a square. Hence, the current enclosed by the closed path is I dash is equal to pi r square by pi a square I, which is equal to r square by a square into I. That is, the portion is I dash is the current that is enclosed by the Amperian path, which is equal to r square by a square into I. As we have discussed, H is again only in a phi direction and depends only on R. So H is equal to H phi a phi, and dl is also in the a phi direction, which is R into d phi. So dl is equal to R into d phi a phi. So by taking H dot dl again, we will get the same answer as earlier, which is equal to H phi R d phi. According to Ampere's circuital law, you are going to equate line integral H dot dl and the current enclosed by the path, which is equal to I dash. So here in this case, when you equate H dot dl to I dash, you get the final answer as H phi into R into integral 0 to 2 pi d phi is equal to R square by a square I. So while integrating and applying limits to phi, you will get H phi into R into 2 pi is equal to R square by a square into I. So our final answer will be I into R by 2 pi a square a phi amperes per meter in the first case where R is less than A. Now consider region 2, where your Amperian path is between your inner and outer conductors, that is in the mid range between A and B. A is less than R is less than B. Consider a circular path which encloses the inner conductor carrying a direct current I. So the path that you are considering is enclosing only your inner conductor and is carrying a direct current I. This is the case of infinitely long conductor along Z axis. So we need not derive that equation further. We already have derived it so many times in the first case also and using the Biot-Savart law also. That is, in this case, H will be always equal to I by 2 pi r a phi, similar to the case of infinitely long straight conductor along Z axis. So the same derivation applies here also. You have to write the answer according to the mark that is asked for your examination. Okay, so here in this case, our H is I by 2 pi r into a phi amperes per meter. Now we moving on to the region 3, that is your Amperian path is within the outer conductor. That is, you know the inner radius of outer conductor is B and outer radius of outer conductor is C. The Amperian path that you are considering is having a radius R and it is assumed to be lying between B and C in our case 3. So in case 3, consider the closed path as shown in the figure, that is figure 7.3 as you can see. The current enclosed by the closed path is only the part of the current minus I. The outer conductor is having current minus I. We discussed that earlier also. The total current minus I is flowing through the cross section pi into C square minus B square, while the closed path encloses the cross section pi into R square minus B square. Now, we already discussed that the portion of the current enclosed by the Amperian path is always taken as the ratio of the cross sections that is enclosed. That is I dash, which is the current enclosed by the Amperian path, is equal to ratio of cross section of the outer path with the cross section of the inner path. That is pi into I dash is equal to pi into R square minus B square by pi into C square minus B square into minus I, which is equal to minus of R square minus B square by C square minus B square into I. That is, we already said the current carried by the outer conductor is minus I. So here you will have a negative term as I dash here. Here you have to consider an important point also, that the Amperian path is already enclosing the inner conductor. Since the Amperian path is in the mid range of the outer conductor, it is enclosing the current that is contained in the inner conductor also. Now you know the current in the inner conductor is I. So I double dash here can be taken as I. So what is the total current enclosed by the path? The current enclosed in the inner conductor plus the current enclosed by the Amperian path. We have derived that the current enclosed by the Amperian path is minus of R square minus B square by C square minus B square into I plus I, which is equal to I into C square minus R square by C square minus B square. According to Ampere's circuital law, line integral H dot dl is equal to I enclosed, that is the current enclosed by the path. Now here also H is again a function of A phi alone and R alone. So H is equal to H phi A phi and dl is equal to R into d phi A phi. So while taking dot product, you will again get H dot dl is equal to H phi into R d phi, which can be equated to I enclosed over the path phi from 0 to 2 pi. So after integration, applying limits and equating H phi, you get the final answer as H phi is equal to I by 2 pi R into C square minus R square by C square minus B square. So H equals H phi A phi, which is equal to I by 2 pi R into C square minus R square by C square minus B square in the direction A phi amperes per meter. Now we will consider the final region, that is outside the cable. Our Amperian path is considered to be outside the cable where R is greater than C. Consider the closed path where R is greater than C. Now, as you can see, the outer path, that is the Amperian path, is enclosing both inner and outer conductors. You know that the inner conductor is carrying a current plus I and the outer conductor is carrying a current minus I. So what is the total current enclosed by the system? Plus I minus I, which is equal to 0 amperes. So when you take line integral H dot dl and equate to I enclosed, you get that line integral H dot dl is equal to 0, which implies magnetic field is equal to 0 amperes per meter. So what is our inference? If the Amperian path is outside the cable, the magnetic field does not exist. The magnetic field does not exist outside the cable, and the variation of magnetic field against R can be represented by the figure. Now consider the figure shown here. We are plotting magnitude of R with respect to R, and the cable is also depicted in the figure. As you can see, in the range from 0 to small a, that is whenever Amperian path is inside our inner conductor, our H is varying proportional to R. So you can see a linear variation of H with respect to R. And whenever Amperian path is between A and B, you can see H is inversely related to R. That is, as the Amperian radius increases, our H, that is our magnetic field, goes on decreasing. And finally, when you reach in the region between B and C, our H is till now varying inversely to R. That is, H is inversely related to R. So here also you can see that our H is decreasing. And finally, when our Amperian path reaches outside the coaxial cable, for example, consider the point C. It encloses both inner and outer conductor. So the total current will be 0. So at point C, our total magnetic field intensity will be 0. So this is the case of coaxial cable. Now consider magnetic field intensity due to infinite sheet of charge. This is our case 3, that is application 3. Consider an infinite sheet of current in the Z is equal to 0 plane and the surface current density K. The current flowing is in the positive y direction, hence K can be written as Ky Ay, and this is shown in the figure. Now consider the path 1, 2, 3, 4 as shown in the figure. The width of the path is B while height is chosen as A. It is perpendicular to the direction of current in the XZ plane. So considering width B, the current enclosed by the path is Ky into B, that is K into delta S. Our width is B, so Ky into B. Now consider magnetic lines of force due to current in the AY direction. It will always be following right hand thumb rule, as you can see. So if you are dealing with two closely spaced conductors, the components of HZ here will get cancelled off, as you can see. All such components cancel each other and hence H cannot have any component in the Z direction. Now since your current is flowing in the Y direction, H cannot have a component in Y direction too. So solely H will be having a component in X direction only. It will not have a component of H in either Y or Z directions. So H is equal to HXAX for Z greater than 0 and H is equal to minus HXAX for Z less than 0. Now applying Ampere's circuital law, integral H dot dl is equal to current enclosed, that is I enclosed. Evaluate the integral along the path 1, 2, 3, 4, 1 as in the earlier figure. Now you can see for path 1 to 2 dl is dz and for path 3 to 4 dl is dz. While you take H dot dl, you will have a term Ax dot Az. Since H is Hxax and dl is dzaz, for paths 1 to 2 and 3 to 4, our line integral term becomes 0. That is H dot dl will be equal to 0. Now consider the path 2 to 3 along with dl, where dl is having a value dxax. Now when you substitute, H for the path is minus hxax and dl is dxax. So finally you get hx outside and integral from the range 2 to 3 dx. So in the range 2 to 3, our value of dx is b. So our final answer is B into Hx. The path 2 to 3 is lying in z less than 0 region, for which h is equal to minus hxax, and the limits from 2 to 3 positive x to negative x. Hence, effective sign of the integral is positive. I hope it is clear. Since the limits are in the range 2 to 3 and 3 to 2 can be interchanged, and hx was minus hxax here, both negative signs cancel off. So our final answer will be positive, that is B into Hx. Now we'll consider our final path, that is path from 4 to 1 along which you can see dl is equal to dxax. And it is in the region z is greater than 0. So when z is greater than 0, what is our answer? H is equal to minus hxax. So here also, like in the earlier case of path 2 to 3, you have a positive sign, where our final answer line integral h dot dl from 4 to 1 will be b into hx. So you have, when you consider 4 paths, you have only value of h in 2 paths, that is from path 2 to 3 and path 4 to 1. Our answer will be Bhx in both the cases. So our total magnetic field intensity will be Bhx plus Bhx, which is equal to 2Bhx. Now for step 5, that is our final step, is to integrate total magnetic field in the contour to the current enclosed by the path. Here the current enclosed by the path is ky into b, and the total magnetic field intensity is 2b into hx. So while equating, you get hx is equal to 1 by 2 into ky. So you know h is having a value only in x direction. So what is our answer? For the region z greater than 0, h is equal to half kyax, and for the region z less than 0, our answer for h is minus half into kyax. So in general, for an infinite sheet of current density k ampere per meter, we can write h is equal to 1 by 2 into k cross an, where an is regarded as the unit vector normal from the current sheet to the point at which h is to be obtained. That is, from the current sheet to the point at which you have to find your magnetic field intensity. So this is our case 3 application for magnetic field intensity for an infinite sheet of charge.